What we've been learning the past day or so is how to write Lewis dot formulas. Okay, Cedrell, let's take that out of your mouth, please. What I told you already these Lewis dot formulas are kind of an accounting method. They don't really show you the actual shape of a molecule. Okay, they're a way of keeping up with how electrons are shared between two atoms in a molecule. All right, or in this case, since we're doing covalent bonding, that's what it shows. The actual shape of a molecule is much different. And so what we're going to begin to do today is use balloon models to start getting an idea of what the shape of a molecule would actually be for something like water and some other things, okay? So I want to remind you of the shape of unhybridized orbitals. In an earlier unit, we made balloon models of p orbitals, if you remember that. I hope you do. Okay, so we found that if you had the nucleus of the atom, then your first primary energy level only has an s sublevel, and that s sublevel has only one orbital, and that one orbital is spherical. Okay? And then when you get to the second primary energy level, there's another s sublevel, and that second s sublevel is also spherical. But then you get to the p sublevel region, and in the p sublevel region, there are p orbitals that are not spherical. They have a double balloon shape. So the way that we chose to represent those was something like this. Okay, so we had these S and P orbitals that look something like this. Now for oxygen has these orbitals like this. Hydrogen does not. The reason hydrogen does not have all these orbitals is hydrogen only has one primary energy level. So it only has this S sublevel down here that's a sphere. Oxygen, on the other hand, has two primary energy levels. And this second level with the S and all these p orbitals, that is oxygen's valence level. That's where all the bonding takes place. Okay? Now, just to remind you, this is an S sublevel. For oxygen, this would be in the second primary energy level. These double balloon shapes are p orbitals. Okay? This might be py. You remember labeling your balloon shapes to show that? This might be px. Yeah, it means it's like on the y-axis of a graph. That's what it means. Okay? It's not more complex than that. It's really conceptually fairly simple. So that would be a px orbital. Yeah, the one that's coming out toward you and back behind, that would be a PZ. Okay? All right? Now, when water actually bonds, when the hydrogen and oxygen atoms actually bond, if we were to take this Lewis dot formula as the way things actually happen, you would think that all the bonds would be 90 degrees from each other. Okay, meaning this angle is 90 degrees from this angle, which is 90 degrees from this angle and 90 degrees from this angle. In fact, that is not at all what happens. Those of you who are talking and not paying attention, I bet it starts to reflect on your grade. Okay, you really need to focus on what I'm trying to teach you and have you learn. All right, So what's going to happen is when bonding takes place, as long as there's no bonding, if these sublevels, these orbitals, were in a lower level, in a larger molecule or larger atom, they would have this sort of arrangement. But when bonding takes place in this second level for oxygen, second level is its valence level, so the bonding takes place in this second level. When bonding takes place covalently, these orbitals change their arrangement and shape. Okay, they're not the same anymore. So what they do is hybridize. There's 5 different types of hybridizations that are reasonably common. We're only going to learn about 3 of them. We'll learn about 3 types of hybridization. And the first we're going to learn about is called an sp3 hybridization. Small letter S, small letter P, superscript 3. So in a hybridization called sp3, we've got a nucleus. This s orbital is no longer going to be spherical. It's not even going to be an s orbital anymore. It's going to become an sp3 orbital. And all sp3 orbitals have a single balloon shape. So the S hybridized, changed its shape, changed its energy, changed its orientation, so that it became a single balloon sort of shape. Okay? This px orbital here is going to change its shape. It's going to change its orientation, change its energy into a single balloon shape. Goes from 2 balloons to 1. This py orbital is going to change its shape, change its change its orientation, change its energy into a single balloon shape. Now, it's kind of hard to tell, but this one is supposed to be like swinging out toward you away from the paper. Because this last orbital, the one that's green in our P and S orbital shapes, is going to be kind of back behind things. So when we hybridize these orbitals in this way, change their shape, energy, and orientation, this is called hybridization, and we're hybridizing to an sp3 hybridized set of orbitals. Okay? And the oxygen and water does this. Going back to our orbital notation, oxygen had this orbital notation. And it becomes an orbital notation that looks something like this. Now, if you're watching the video, we're not going to arrange these orbitals in energy stages. We're just going to arrange them horizontally for this class at this time. So what happens is the S and P orbitals become a new set of orbitals here. 1s doesn't change, but the second primary energy level, where these electrons are located, that's water's valence level because that's its highest energy level. The highest energy level electrons, in order for covalent bonding to take place, these all change into a new set of orbitals called sp3. So in their second level, this is sp3. They all have the same energy, and they have different orientations, but the same shape. And so they're like all the same. So they're not separate groups now. They're the same kind of orbital. We're going to use our sort of school bus rule system for filling the orbitals. So this is the orbital notation for oxygen. 1s here is the small sphere inside. 2s is this big shape here, for at least for oxygen it is. 2s is the valence level. 2p, those three boxes are represented by these double balloon shapes. All of those change their orientation and shape, so they become sp3s. So like each one of these four boxes is represented by each one of these four balloons. The angle on each of these balloons, if you were to draw, say take a big sharp needle that went right down through the very tip end of every balloon on the top to the center, the angle between each one of those needles would be 109.5 degrees apart. And we'll talk more about that later. Right now we're going to make this model. You're going to choose a partner. Well, you and one other person are going to make this model. So get out 4 round balloons. You're going to blow them up the same size. The balloons have to have different colors. Blow them up the same size. Tie 2 balloons together. Tie 2 other balloons together, and then you can put the whole thing together. Are you listening to me? Tie 2 balloons together. Tie 2 other balloons together, and then it's really easy to put the 2 sets together. Okay?
Can we move around the room?
You can move around the room if you want to, yes.
Hey, Frank, you want to